In this video we'll collect and recognize various patterns produced by Riemann's zeta function. They might give some insights and open paths forward to help solving Riemann's hypothesis. This is the same plot shown in previous video, which was taken from Wikipedia, to illustrate the position of first non-trivial zeros along the critical line. Wolfram Alpha provides online tool to make the same plot interactively. Note that the color convention is different than from Wikipedia. Here the real part is blue while the imaginary part is orange. It shows that the real part has reflectional symmetry, while the imaginary part has rotational symmetry. Riemann's hypothesis concerns with non-trivial zeros of zeta function other than those on the critical line. Let's see how shifting the plot of zeta function from critical line to its shape. In general, increase of the real part for the input of zeta function reduces the amplitude of the plot, while decreasing the real part increases the amplitude of the plot. The equilibrium of the real part of the zeta function's output is 1, while for the imaginary part, it's 0. The absolute of zeta function shows its distance from the point of origin. It can show more clearly where the positions of non-trivial zeros. Since it's symmetrical about the real line, we only need to plot the positive imaginary part. In general, shifting away from the critical line drives the plot of zeta function further from 0. This is the list of the first 40 non-trivial zeros of zeta function. All of them lies on the critical line, that is, their real part is half. The irrational numbers shown here are the imaginary part of those zeros. A pattern seen here is that the difference between adjacent zeros look random, but they tend to get smaller as the imaginary part gets higher. Here are the plot of first 100 and first 1000 non-trivial zeros of zeta function. The curves look smoother for higher number of zeros shown in one plot. The pattern may have correlation with the distribution of prime numbers. But it doesn't seem to be useful in proving Riemann's hypothesis, which says that non-trivial zeros of zeta function can only be located on the critical line. That's why we need to explore the behavior of Riemann's zeta function outside of the critical line, by plotting it along the real part of its input with a constant imaginary part. We only consider the real part between 0 and 1, because it's the relevant area to the Riemann's hypothesis. At non-trivial zeros of zeta function, the real curve and the imaginary curve crosses 0 when the real part is a half. At a glance, there seems to be no obvious pattern which is useful to prove Riemann's hypothesis. So, our goal for the next videos is to find a process to filter out irregularities and extract regular patterns in Riemann's zeta function. This process can be done by using functional equation and the relationship between zeta function and its conjugate. Functional equation relates values of the Riemann zeta function at the points s and 1 minus s, while the conjugate equation implies that the zeros of the Riemann zeta function are symmetric about the real axis. Combining them implies that the non-trivial zeros are symmetric about the critical line real part of s equals a half.